Start. So, what I wanted to talk about was first, there are some aspects that are essential when we are talking about or when we are talking in terms of AMO physics. Um, that we are always dealing with frequencies and measurements of very narrow transitions or specific atomic systems. So, in that, it's also required that there are some factors or like some constants that are really essential. And when when you're talking about those, um, so what do I mean by so when we are talking about energies in quantum physics or atomic physics, we are generally talking about energies in terms of quantized states, and each of these states or each of these energy levels is generally represented by h nu or h bar omega. So whenever we are talking about energy, we can talk about energy in terms of just frequency, or we can talk about energy in terms of angular frequency, because our basic system is like a nucleus and electron is going around. So the concept, like in last two lectures also, we emphasized on this a lot, that how angular frequency, like simple harmonic oscillation and circular motion is connected, and how we can connect everything together by either a harmonic oscillator or a two-level system that we covered in the previous lectures. So when we are talking about frequencies and we are talking about angular frequencies, there is a factor of 2 pi in between. So whenever we are talking about angular frequencies, generally in atomic physics, we represent them by omega. We represent them by omega, and there is a factor of 2 pi in between uh, in frequencies and angular frequencies. If I mean, this is very obvious, but the factor of 2 pi generally comes at a lot of places, and generally in derivations also, or even in numericals, you miss that factor of 2 pi sometimes, and then that scrambles up your calculations too. So always remember that whenever you are talking about omegas in this course, if you see a symbol omega, we will be always talking about angular frequencies. And if we are talking about just frequencies, which is in the units of hertz, which is 1/2. And if we are talking about omega, then it is radians per second. So it by looking at the symbol as well, even if I miss a factor of 2 here and there, a factor of 2 pi here and there, you should understand that whenever I am writing omega, it will be an angular frequency. And whenever I'm talking about f, or people also use f, or people also use nu for just frequencies. So if you see these two, then it is just a frequency, and if you see an omega, then it's angular frequency always in this course. Um, Another thing we will be talking a lot about frequencies, wavelengths, and speed of light. We all know this relation that c is equal to n lambda. That relates the speed of light with frequency and the wavelength. So where we can also write this as nu lambda. That is the frequency and wavelength. So we'll be using this relation a lot. So remember that frequency and wavelength are, of course, related, and the relation is through the speed of light. Whenever we are talking about numbers, in physics, it's really good habit to have like a feel for the numbers. So, and also the dimensions of the numbers. So then if I say omega, what is the dimension of omega? What are the units in which we represent omega? If I'm talking about frequency, what is the unit of frequency, time, energy unit, and basically the dimensional analysis, I think, is like the first thing that you learn in physics, and that's really important, especially in AMO physics, because here you're doing precision experiments in the sense that each small factor matters a lot when you're measuring something, measuring, let's say, atomic resonance. Um, because atomic systems are used nowadays as the most precise clocks, along with some other systems. So whenever you are measuring something, you have to measure it with really good accuracy, and you have to know all the factors that are present in your calculation. In order to do that, you need to not miss any factors, and you need to have like a feel for numbers. So what do I mean by feel for numbers is we are doing conversions a lot, always from wavelength to frequencies and some other quantities, but mainly wavelength and frequencies. So whenever we are talking about lasers, we can talk about either the laser's wavelength or the laser's frequency, which will be the fundamental frequency in which it will emit. So as we all know that 400 nanometer to 700 nanometer is the visible region of light. So it's good to remember that uh, roughly 300 nanometers is 10 to the 15 hertz, which is like a terahertz. So all like 400, 600 would be 1 over 2, a factor of 2 from terahertz, but the order of magnitude is terahertz whenever we are talking about hundreds of nanometers. And it's good to remember that because you are always converting in terms of from wavelength to frequencies and from frequencies to wavelengths, etc. But you are always kind of dealing with if you're dealing with visible transitions in the visible range, basically if the atom emits a photon, and if you can see the photon, then that photon is roughly in 400 to 700 nanometer region, which is the visible spectrum. Below that is infrared, above that is X-rays, and yeah, that's all is above that is UV, and that's all is well known. But what I'm trying to emphasize is if you remember like a certain number, if someone says that, okay, I have a terahertz laser, what does that mean? If you are familiar with talking about lasers in terms of wavelengths, it's good to remember this conversion. So if someone says they have 600 nanometer laser, you can already in your mind remember that, okay, then it might be of the half of the terahertz or something. So you already have like a frequency in your mind which you associate with that wavelength. Because whenever we are talking about specific transitions and we want to, let's say, determine the frequency of the laser, keep it locked, keep it at this exact same frequency, know that how much the laser deviates from that frequency, which is like the width of your measurement. So whenever you're talking in that regard, you need to know about, you need to talk in terms of frequency. And whenever you're talking in terms of wavelengths, let's say how much is your diffraction limit, how much is the spatial extension for your laser, for the laser pointer or any spot that you are measuring in the experiment, then you have to, whenever you're talking about spatial extent, you have to now talk about wavelengths. So wavelengths kind of give you like the spatial information about the laser, and frequencies, of course, give you that atomic response. So you'll need to talk a lot about lasers in terms of either wavelengths and frequencies. So it's very useful to remember this conversion. And this actually was also mentioned in the Wolfgang lectures that I have been telling you guys about. That this entire series is actually based a lot on Wolfgang's lectures that are available on YouTube. So he also emphasizes the fact that you need to remember certain. It's not like you need to remember, because of course you can just Google anytime. But it's if you remember those, then it's really, it gives you an edge while calculating something offhand or back of the envelope calculation. So yeah, I just wanted to mention that 300 nanometers is same as is roughly equal to, maybe roughly, I don't have the exact conversion here, but maybe roughly equal to a terahertz. So that's good to remember. Then last in the last lecture, I think we talked about quality factor. Um, if not, I think every oscillator that is oscillating has a quality factor associated with it. And the quality factor definition is pretty simple actually. It's just the frequency at which it is oscillating divided by the width of that uh, spectrum or the width of that resonance. So the oscillator has a resonance at, let's say, a frequency f naught. Then the quality factor for that oscillation or for that oscillator is just f divided by the width of that resonance. What this gives you is quality factor. Physically, what that means is how many oscillations you can measure um, in 1 second, or how many oscillations you can quantify that system for, because that gives you the accuracy. So the one divided by the quality factor will give you the accuracy of the system. So the most precise atomic clocks roughly deal with quality factors of like 10 to the 18 or something, close to 10 to the 18, or maybe I'm off by a order of magnitude or so, but generally, we have talked about terahertz. So generally, the lasers are in terahertz, and if you imagine, then if the width, uh, be, because you can also see that quality factor is dimensionless because f is also in frequency, and change in f, the width is also in frequency. So both of them will be hertz, and if you take a ratio, that will be dimensionless. So quality factor is always dimensionless, but it describes how precisely you can measure something in an oscillator. So and what's the limit of your system? So in atomic clocks, generally, I think the limit, maybe it's more than this, or maybe it's order of magnitude around this, but it's roughly 10 to the 18. And how we get 10 to the 18 is you can see it like this, that if you have f as a terahertz, 1 terahertz, and you have a 1 millihertz lock, which is like the width of your resonance is like 1 millihertz, which is extremely narrow. It is not at all. It is not at all regular. That in normal systems you won't see such narrow lock. By no lock, I mean the width of the resonance is not as narrow. Generally, the width of resonance is in megahertz and not in millihertz. For atomic systems, generally the natural width of any transition is roughly in like megahertz. But there are systems where we can manipulate the laser, and we can manipulate the lock basically, and we can make the laser stable uh, to a point where the width of that resonance is in millihertz, which is incredible, which is like which is almost like the edge of the science in terms of how narrow we can make the width of the resonance. So, but if the width is millihertz, then that is 10 to the minus 3 in the denominator. And in the numerator, you have roughly terahertz, which is 10 to the 15. So 10 to the 15 and 10 to the minus 3 in the denominator together gives you a quality factor of 10 to the 18, which is extremely high quality factor. And these are roughly like the systems that people use in atomic clocks, or very precise experiments, or in such systems. Basically, you get such high quality factors. So it's the quality factor is also like a good parameter to know, or like a good quantity to remember while talking about oscillators, especially because that's how you can compare different oscillators, and depending on whatever applications you have, you can then choose the oscillators. But anyway, so we talked about angular frequency, we talked about quality factors, we talked about wavelength and frequency numbers. Okay, I won't talk about atomic units, but the language that people speak in atomic physics is generally atomic units, because all those constants that are lying around, you can just make them disappear, and talk about only the numbers that matter in terms of transitions and in terms of the energy levels. So if you take hydrogen atom, and everything about hydrogen atom is known. Um, and also hydrogen is actually the only atom which we can solve exactly, and all the atoms above that we can't solve exactly because there are more than one number of electrons. So that is all well known. So that's why we in atomic physics, what we do is we make hydrogen atom our base, and all the quantities that are associated with hydrogen atom, let's say the energy line and the electrons first orbit wavelength and radius and everything. So all the quantities that we get from hydrogen atom, which is exactly solvable, we make all of them uh, very well known, and those are we normalize other systems using those. So it's like we represent other systems in terms of the parameters of hydrogen atom. So that's I think the motivation behind atomic units, and there's a lot of literature, and atomic units are actually very well known since ages. So then you can also see for yourself what exactly are atomic units, and make sure that you're familiar with them, because this is like a really important important uh, ingredient to have when you are studying atomic physics. So yeah, okay. Atomic units is like the language which atomic people speak in. And we already talked about having the feel for numbers, and which constants are really important. And if you basically if you see h bar, then of course all the time with h bar there will be omega associated with it. If you're writing energy, then if you see h bar, there will be omega alongside it. If you see h, then there will be nu alongside it, which is the frequency, which will make an energy. So it's like if you see h, you should automatically write nu or f alongside it and not omega, so that you'll not get confused between these two pi factors, because they get little annoying if you are in a hurry and if you are making some calculation, and then like just a factor of 2 pi will scramble the calculation, which is not great. So okay, so that's why there's the feel for number. And okay, the final thing is this is what generally we understand when we do detailed analysis of any system, is that first we need to understand the system fully in order to get any application out of it. So atomic physics earlier in like early 90s, or sorry, not early 90s, maybe 19th century, people were only using atomic physics generally to study them, to understand them perfectly, because they were not as well known as they are today. So that's why the limitations of the knowledge of your system will also prohibit you from using it for applications that are all possible with that system. So once you understand the system fully, then you can apply it, then you can control it, then you can manipulate that system. So actually the knowledge, the understanding of that system is the first step before you can apply that system anywhere else. So this is what happened in atomic physics, I think, atomic and molecular physics, that people didn't know 100%, or people didn't know a lot about light atom interactions, let's say, or atomic physics, molecular physics. But once they started to know the structure, once they understood the theory completely, then I think the control of atoms and the manipulation of atoms and light then started, because the first step is to understand the system fully, and then we can apply you can use that system as an application. So if you see any system that is used as an application, which is like now the atomic system is used as an application. So lasers are made out of like solid state gas. There are systems which currently work. So I think the research is also going on in single photon emitters. There are like fancy things going on with where we manipulate light, we manipulate atoms, we control light, we control the atoms, and that this is possible only because we have understood completely the system of atom and light, um, which is like the basis of this course. But yeah, that is like a motivation point, that controlling a system or manipulating it for an application first requires you to understand the system fully and get all the knowledge that is there inside in the system. Because whichever system, whatever is the extent of your knowledge, only that you can use it for application. So Anyway, but yeah, this was short section. I just wanted to tell you a few points that you need to know as like a person working in AMO, atomic molecular optical physics. But we'll move on to the next section, which is okay. I now want to talk about lasers because we use lasers a lot in the lab. So I am also an experimental physicist. So in I do experiments. When I do experiments, I have we generally do light atom interactions. We control the atoms using light. We interact light with atoms. We manipulate atoms with light. We cool them down. We trap them. Everything with light, focused light, and collimated light. So that's why it's really important for us, or even for theory people, to understand laser, because laser is a special kind of a light source, and we can't just use any other light source in our experiment. It has to be a laser. So that's why I wanted to motivate why we use lasers or how lasers work. I think the fundamental principle and everything is very well known, since this ha this topic has been taught, I'm sure, in even undergrad and grad physics. But still, I want to talk a few minutes on it. So of course, what's the working principle of lasers? It's in the full form itself. Full form is light amplification by stimulated emission of radiation. So last time we talked about stimulated uh, emission and absorption process and spontaneous emission process. So there are only two main processes that are happening when you are exciting an atom or exciting a two level, let's say. You can either have stimulated absorption and emission. The word stimulated basically means that you are incidenting some energy on the system, and then you are carrying out the transition. So whether it's an absorption, so if you are making the electron go from the ground state to the excited state, that is stimulated absorption. And whether you are making the system come from the excited state to the ground state, it is stimulated emission. But there is, in addition to these two, there is also a process of spontaneous emission, that even if we don't carry out the process of electron coming back from excited state to the ground state, it will eventually come back because of the vacuum fluctuations. And that process is spontaneous emission, which even though we don't carry out, it still gets carried out because of the fluctuations that are present and because of the instability of the excited state. So these are the three processes that are there in the nature, and from these processes, stimulated absorption and stimulated emission, I think these two processes, along with spontaneous emission, we use them in tandem to get laser working. Um, the basic principle behind, or the basic formalism behind lasers is basically, first you do population inversion. That's how it is from the start. If we want to learn about lasers, this is how we learn it. That we have a two-level system. We have a ground state and an excited state. But actually, lasers are not possible most of the time. When you are dealing with lasers, you are not dealing with just two levels. There is also another level, which is like metastable level. Um, we haven't talked about three-level systems, so just take it on faith that okay, if we have a third level, and which is like a metastable state, then we excite first from the ground state to the excited state, and the excited state then decays down to the metastable state, which is the metastable state. So it will be there unless it gets a push, and that push is what we provide via single photon. And then, since all different atoms are gathered, or different electrons in one system, which is like how solid state laser works. So then if all the population basically of electrons is in that metastable state, which happens by either optical pumping or some kind of pumping, which is how we generate the gain, which is how we generate the amplification in the laser. So if we excite everything to the metastable state, then we incident a photon, and that photon's frequency, if it matches with the transition frequency, then we get an emission, which is amplified emission uh, of h nu frequency, which is the frequency difference between the two levels. So that is generally the principle behind lasing action. That first you need a gain medium. In that gain medium can be anything. It can be a solid, it can be a gas, it can be a plasma. Um, I don't know anything else, any other gain medium, but maybe these three. So once you have a gain medium, you basically pump it to a state where now it's ready to emit a lot of radiation. Whether it's ready to a lot of energy is basically stored in now in that medium. And then now you if you give it a push, which is like, by push what I mean is you incident some energy of correct frequency, then you can emit a large amount of radiation, which all of it will be exactly same frequency and exactly same phase, which is the specialty about lasers. So the special thing about lasers is like they are coherent sources. We can't use random incoherent thermal light that we generally get from bulbs or anything else. That we can't use for experiments because whenever we are doing experiments, we like to do experiments with certain parameters or certain probes that we know for sure that okay, these are not going to change over time, these are not going to change over the space of the experiment, these are not going to these are going to be well defined probes basically. So such probes are lasers for us in atomic physics, or even in solid state physics actually lasers are used. So this is the idea behind the laser, that it's a coherent light source. It outputs a narrow beam, a diffraction limited beam. What do we mean by diffraction limited? Is the if you want to focus a beam down, then the spot is so narrow that now you have to also consider the effects of wave nature of light. You can't go narrower than that in that uh, in that particular system. And if you go at that limit, then you'll also have to consider the wave nature of light, which is like you'll get all sorts of interferences, and you'll get diffraction patterns. So that is the limit to which you can now approximate your system, and you can't go below than that. So that's like the diffraction limited beam is how narrow you can make a real beam in this in the real world, because after that, beyond that, there are interference effects that happen. So whenever we are doing experiments, whenever we are focusing down a laser, the limit to which we want to focus it down is like the diffraction limit. And diffraction limit, you can read about diffraction limit, but it is like the limit where it's a fundamental limit which comes from uncertainty and everything. And it is the main idea is that light also has a wave nature, and that the push, or like the limit to which we can extend that, or limit to which we can ignore that wave nature, is like the diffraction limit. So it the laser is a source which is like a coherent source with narrow beam that has an ability to produce a diffraction limited beam. And laser can be, of course, a pulse laser or a continuous laser. So I'm not going to go in very detail, but yeah. So at the start of the lecture, I actually had a poll in which I asked that is it necessary to have population inversion when we are doing lasing? So in most of the system, yes, it is necessary, and all of the systems that are used for lasers in general, it is completely a step that population inversion is definitely there in all the lasers. But like theoretically, if we need to talk in terms of is lasing possible without population inversion as well, generally it's not used. Generally, population inversion is how you get lasing, and in all the systems that we use in the lab, population inversion is used. But if you want to think just conceptually or theoretically, is it possible to get lasing without population inversion? Then yes, the answer is I think yes, you can get it without population inversion. In there are two cases where I know this is true, which is one of them is EIT. I'm not going to talk about these two because these two are like very um, detailed fundamental topics in quantum applications of like quantum optics or atomic physics. It's like it's very detailed subject, but and these are very specific processes that people use in the lab for manipulation. In like this is for at the forefront of the research. Actually, both of these topics are the topics and on which our lab specifically also researches on. So but in order to reach that stage, we will have to talk about a lot of things first in the course. So I'm not going to explain these, but I'm just mentioning them so that in future we can talk about. Yes, I'm going to write the full form of EIT. EIT is electromagnetically induced transparency, and this is first, and this is second system, which is super radiance. So actually, just let me tell you in 2 or 3 sentences what's the idea behind this. So what do I mean by population inversion is not necessary for lasing? So then what is the necessary condition for lasing? So it's like if you see lasing as there, you can also see lasing as the following. So you can see lasing as the imbalance between the absorption of your system and the emission of your system. So what population inversion does is basically it creates an imbalance between the absorption and the emission. So you get an amplified response. So what you are doing here is you're suppressing your absorption and you're enhancing your uh, emission. So this imbalance is what is the necessary condition for lasing. That if you have this imbalance, that your absorption is pretty less and your emission is pretty more for a given system at a specific time, then you can get lasing out of that system. So that's like the more necessary condition if we really want to technically talk about lasing. Then more than population inversion, the imbalance between the absorption and emission is at more fundamental level the necessary condition for lasing. So now, if we can find a way, if we can find some tricks in our system where we can deplete our absorption, we can decrease our absorption as compared to the emission. So if the emission profile is the same for our system, if we keep emission profile the same for our system, we change nothing about the emission profile. And if we only change the absorption of our system, in the case that if we decrease the absorption of our system, somehow if we are able to manipulate absorption of our system, the coefficient of absorption or anything like uh, it's I'm talking on very surface level because detailed discussions of these are is available on internet. If you are at a level where you can understand them, then please understand them. Electromagnetically induced transparency is responsible in a way to decrease the absorption of the system by creating dark states, by creating states which cannot be excited uh, by a specific by specific light or by whatever specific radiation that you have, let's say. So you can create levels in your atoms which are dark, which you can optically pump to. By dark, I mean they cannot be excited by the light, by a specific light that you are incidenting. So that is the technique that people use in electromagnetically induced transparency, where they create the atomic levels by having interference between the original levels, and they basically decrease the absorption of the system in with regards to the specific levels. That's how they can create lasing, is they can decrease the absorption and emission is the same. They have not altered the emission. So then this imbalance is created and now you can have lasing in your system. There is another way that you can have lasing in your system is if you don't change absorption of your system at all, but you manipulate the emission. In the first case, when we were talking about absorption, decreasing the absorption, in that case, atomic levels were interfering with each other to cancel out each other's effect, and that's why you were getting less absorption by dark states. Now you can also get higher emission by super radiance, in which the emitted photons, the spontaneously emitted photons from 2 different atoms, are now interfering to give you uh, like a greater, like by interfering you will get higher emission. If they together emit collectively, then the collective excitation of uh, two atoms, three atoms, or n number of atoms, if they collectively excite, if all the photons that are emitting from these atoms are interfering, then you can get a branch of that emission where you have lot of emission, much more than what you would get if the n atoms were not interacting. So the fact that the n atoms are interacting in terms of the photons that they are emitting. So if the photons they are emitting are entangled with each other, which is like they are interfering with each other, then you can create a state where you can get lasing because you have much more emission compared to the absorption of the system. But anyway, I'm not going to talk much about these two systems, but just I just wanted to mention them because it's a really nice point. I appreciated this point recently when I was studying these two phenomena, that you can actually theoretically think of lasing without population inversion, because lasing is more about, if you think really theoretically and conceptually, it is more about the imbalance between the absorption and emission of your system. So you can get lasing without population inversion in theory, but experimentally, most of the systems that we have in the lab, most of the systems that people use in industry or research labs, not most, maybe all of them, have they involve population inversion, and population inversion is like the regular route how people get lasing. But I just wanted to mention this point that maybe it's not completely necessary to have population inversion to get lasing. But anyway, um, and also another interesting point, which maybe I will cover later, or it's again a detailed topic. But since we were talking about focusing now down the light, or we also talked about diffraction patterns. Actually, Fourier transforms is mathematically something that you can really use. Fourier transform concept, going from frequency space to time space or vice versa. Like basically changing your space, uh, which is how we also talk about uncertainty principle, how that is also related. Any two conjugate variable spaces, you can go between one of them. Um, you can exchange the spaces. Basically, you can transform from one space to another space. That Fourier transform concept, which is mathematical and which has great applications in all the signal analysis and everything, those are really related. Those are very closely related to these two concepts of diffraction, getting a diffraction from like a slit, and a focus, like focusing down a beam. So it is it there is, I mean, you can find it on Wikipedia as well, that the field which connects all these concepts is called as Fourier optics. So in optics also you can approximate. So it's like if you have um, a lens in between, and if you incident something on the lens, and you get a focused light, and then at the focus you can imagine the focus is one focal length away from the lens, let's say. Then the focal point is like a Fourier transform of the one focal length behind the lens, whichever object, not object, maybe an object as well, but like the focal plane, basically the point is a Fourier transform of whatever image that you're taking. So if you have a laser, then you can take Fourier transforms. You can convert, you can think in terms of different spaces, like spatial domain. In material science, people talk a lot about K space, which is like the wave vector space. So you can think in terms of momentum spaces. You can think in terms of spatial modes of light, as opposed to temporal modes. Like time is generally how we imagine all these things. But you can go from one space to another space, even experimentally, and these concepts can be understood actually in terms of Fourier transforms as well. Uh, like so, like the focal point basically is a Fourier transform of the initial object or initial laser that we were sending in. That's like the surface level thing. Again, also diffraction pattern. So it's like if we are taking a diffraction through a single slit, then the pattern that we see is like a Fourier transform of that slit. So again, these things I will not talk a lot about them, but these are very interesting things. These are the things basically that fascinate us. And if you are at that level where you can read about these things, or you can understand these things, then please do. Fourier optics is really like a great it's a great field to learn about when you're working even in the lab, or if you are working in an AMO physics. Then it's a really nice illustration of how you can use Fourier transform, or again an illustration of maybe why Fourier series and Fourier transform is such a fundamental thing in physics. Um, it's like a basis set in which you can explain everything. So that's why I wanted to just mention once that Fourier optics is another field which connects diffraction, which connects for focusing down a beam, connects these two concepts, which are very fundamental, which are very experimental things that we do in the lab, with the Fourier transform theory, which is like generally how people understand everything theoretically, or explain signal analysis in terms of. These three are very connected though, and the connection is we can find the connection in Fourier optics theory. So anyone, if they are interested, I don't think we will have a lot of time maybe to talk about these things in the course, but yeah, if we get time, if anyone is interested, I can provide you the sources as well. Because in this course, in addition to light atom interactions, like specific derivation, I also wanted to tell you like what are the aspects that people are in general interested in, what are the aspects that people do research on currently in the field. So these three concepts, which I am saying a lot about in like last 10 minutes, this is not generally what we will talk about a lot, but some of this is well understood. I think most of this is well understood, but it is relatively very new. These fields are relatively new, and these are not generally the fields that, or these are not generally the concepts that people talk about in their masters or something, because these are even now a little less understood or less appreciated phenomena, which are relatively new in last 50 years or so. And maybe Fourier optics is a little older, but still, these are very interesting concepts. And if you are at a level where you can understand them, then please, these are really interesting systems. And why I have written SLM. SLM is a spatial light modulator, and that's a device that we use in the lab, in the experimental lab, to manipulate phase and amplitude of the light, of the laser light, by using the concepts of Fourier transforms. So experimentally, if you want to see Fourier optics in working in the lab, then SLM is one of the device that at the core uses this concept of Fourier transform and connects like diffraction patterns with focusing down lights with Fourier transforms, connects all this and illustrates it in a picture. And maybe when I talk about in the last one or two lectures in this course, when I talk about what research I do in the lab, maybe at that point I will talk more about these systems. But SLM, spatial light modulator, is the device using which we manipulate like phase and amplitude of the light, and which involves inherently the concept of Fourier optics. But yeah, more on that maybe later. So coming back to lasers, why is laser such an important source? Uh, to talk about that, we can also talk about temporal and spatial coherence. Uh, coherence is a term which is used a lot in quantum mechanics, which you can, I mean, sort of here, what I wanted to emphasize was coherence means like having the same phase. That phase can be spatial, phase in the sense that having um, okay, maybe phase, yes. So because generally how we see when two waves are in coherent, when two waves are coherent, they say that when the phase is the same, exact same, right? Because if you imagine light as an electromagnetic wave, then it basically has just three or four parameters that we always talk about. One is the amplitude, then is the frequency, and then it's the phase of the beam, or it's like the polarization. There are like four or five different things that we talk about, because we can write it as a e to the power I omega t plus phi. So then in that case, phi is the phase, omega is the frequency. Now, um, Even you can see here, I have written omega. So remember that this is the angular frequency. So it will be 2 pi times f. So I won't repeat that a lot in the course, but always remember if I'm writing omega, I mean to write 2 pi f. So, but anyway, that's how generally people use it. And this is the amplitude. There is also a polarization. So these are like the 4 or 5 things that maybe I'm missing one, but these are like the 4 or 5 things that we manipulate in the lab always when we are working with atomic physics and light. So light, if you imagine as electromagnetic wave, or even as a photon, you can think of uh, what we are manipulating about light. We are either manipulating its polarization, we are either manipulating the amplitude of the light's oscillation, we are either manipulating the frequency of the light, or we are manipulating the phase of the light. So then, what are these two coherences in this regard? What is temporal coherence and what is spatial coherence? Because these two coherent systems, like these two coherences, is what are the things that makes lasers special. So, and because the light that is emitted in the laser is both spatially coherent and temporally coherent. How much it is spatially coherent and how much it is temporally coherent depends on your application, depends on the specific laser. But both these concepts are used in every laser that you see. So what is spatial coherence? Spatial coherence helps us in focusing anything down to a narrow spot. So by what do I mean? It has specific spatial mode. What do I mean by that? Is basically if you have a light source like this, and if this exactly matches, if this exactly matches with the system, if the two waves that are coming out of the laser, if you can imagine two photons, or you can imagine the two waves coming out of the laser, because again, you can imagine in terms of light nature, you can imagine light in terms of particle nature or wave nature. But make sure that you understand the concepts of spatial coherence, that if they are spatially coherent, then basically now if you want to focus this light down to a narrow spot, it will be possible to focus it down to a narrow spot. But if these two are not the same, if this and this, uh, these two waves are not coherent in space, then if they are having a mismatch basically, then what will happen is that is known as aberration. So then if the focus basically, if they are not coherent, then the focus will shift, and we won't get as narrow focus as that is possible. That is possible using a coherent laser, spatially coherent laser. So by spatial coherence, what we mean is each wave that is coming out of the laser is coherent, and spatially it has the exact same profile. It has exact same wavelength. Having exact same wavelength is monochromatic. Having exact same phase is coherence. So if you have a source which is laser, then the outcoming light or the outcoming stream of photons, they are all spatially coherent. And what what's the use of that is we can focus it down to a narrow spot which is diffraction limited. So and any other uh, any other laser or any other light source that if you take, then that light source cannot be made more narrower than this coherent source, because the narrow or the short spatial overlap that you can have, the smallest spatial overlap that you can have in the focus is diffraction limited, and you can reach the diffraction limit, or you can reach how small the focus spot, how small the focus can you make using a laser source or using a light source, will depend on how much coherence you have, how spatial coherence you have. So spatial coherence basically gives you this ability to focus it down to a very narrow spot, and that is only possible when you have spatial coherence. Um, in more technical term, it is called as specific spatial mode. When we consider light electromagnetic wave in terms of transverse modes, you can also think that you can produce specific spatial modes in the using a laser because of the spatial coherence. So the spatial coherence basically gives lasers how white light focus. What's do you want to comment on that by unmuting yourself, Nitin?
Hi, I just want to know that if the spatial coherence means defined by the focusing of light, then normally we use lenses to focus white light also. That means the focus of the white light is not highly focused, or like, I don't get that meaning here with the spatial coherence with the lens example.
Um, in case of white light, um, also this is true. But I think there are two things here, which I'm also not 100% sure about. But there are two things here that one is having a very narrow spot and one is having exact same wavelength as well. So you can have different modes of light in the sense that you can have different frequencies and also you can have different emission modes. So in white light, of course, there are all wavelengths are present, but it is composed of all the wavelengths. But yeah, spatially, it is possible to focus it down to a narrow spot, but whether it is diffraction limited or not, that I will have to check because
Okay.
whatever lasers that we use in the lab are all monochromatic, like they have exact same wavelength, exact same frequency. So then we definitely say that they are diffraction limited. I don't know about white light sources, but yeah, that's an
I mean
interesting
to,
question.
sorry for interruption. I mean to ask is like if you have a same lens, like which is perfect lens, let's say, if you illuminate with the laser source, it give one size of spot, and the same lens is again illuminate with the white light source. So the both the spot from white light and the laser have a same size of spot width, or they have a
I
different.
I think they will have different widths because intuitively, as I can imagine, your how much you will deflect will depend on your wavelength or your frequency because I mean speed of light is changed depending on whatever your frequency is in a medium, and then because air is a medium, so then if you have a different wavelength light source, then all of them will deviate, and it's like I think different spots will converge on different points in space if I'm imagining right now, just as a back of the envelope intuition. So I think if you have multiple wavelengths together in a laser, then maybe microscopically,
But then
uh,
it's about the polychromatic nature and the monochromatic nature, and how it is especially coherence.
um, yeah, that's true. Um,
Because that is like a different achromatic aberration reason, like because a different wavelength have a different refractive index in the medium, and that's why they have a spread in the spot pattern. So
right.
that come from the polychromatic nature of the light, not from the spatial coherence. So I'm just confused with the spatial coherence reasoning here, so that's why I asked this
Oh,
question.
so monochromatic, having monochromatic light, is it related to then temporal coherence, you think?
I'm not sure, but if you have monochromatic light, you still not have the light source can be spatially incoherent also.
Right,
Having monochromacy is not mean that it has a spatially coherence.
right. But yeah, I'm trying to understand then is it in terms of temporal coherence then, or monochromaticity is completely different than these two coherences, spatial and temporal coherence.
Basically, what I remember from my understanding is coherence basically come when the we have a fixed phase difference or a fixed phase under mathematically representative of phase.
Hmm.
So if it is have a exact phase or a fixed phase difference, it will give a coherencity. In spatially coherence, like two different spatial part of the wave have a fixed mathematical representation with each other. That's why
Hmm.
I understand. So that's why I also confused whether I can ask this question or not, because
Uh, no, I mean, yeah, I because these two concepts, I mean, why even I mentioned them because whenever I mention laser, these days I think these two concepts are very important to mention,
True,
because
complete. This to define the
they,
lasers actually, yes.
yeah, they are even present in the Wikipedia article on the
Correct,
in the
correct.
first page. So it's like that's why I wanted to even understand. So because actually understanding spatial coherence and temporal coherence comes much later in the in any like quantum physics course, or even
I
in
agree, I
because
agree.
coherence concept is little involved. But it's like
Correct.
lasers we study mostly. I have people have studied
Mm-hmm.
starting from 12th or something.
True, true.
But yeah, I mean, it's an interesting point. I don't know the answer, but I will find out. Maybe I'll find out
It's
and
fine. No, no. I just asked because we are discussing about the spatial coherence,
no, yeah,
and
it's a valid question.
yeah,
It's a valid
yes,
question.
yes. So that's why I just try to ask this question. Thank you. No
Yeah.
problem. Thank you, sir.
So actually, so what makes then the laser source special is that we can focus it down to a very narrow spot. But yeah, we can resolve that issue. How exactly that is related to spatial coherence? Maybe it's not, but so spatial coherence allows us, or maybe the light source has this ability to focus down to a very narrow spot. And it also has the ability, in addition to focus, it also has the ability to collimate itself. Uh, be collimate, stay collimated in for a long time, or for a long length. That is again called as coherence length. But I guess whenever we talk about coherence, the understanding becomes involved. So then, but still, I wanted to mention this once. So you can also have collimation, which is like uh, making the light go from one point to another point without changing its frequency, without changing the phase, and without changing the size of the spot. So if you have, like, say, a 1 micrometer beam, or maybe micrometer is too small, let's say, millimeter beam. So if you have a 1 millimeter beam spot, then that spot should stay 1 millimeter exactly in radius, if and also have the same polarization, have the same phase whenever it's moving from point A to point B. And for how long it can do that, that is also a part of, I guess, spatial coherence. That so basically, in laser, you can focus it down to a narrow spot, and you can also collimate the beam to a very large distances. That those are the two special things. And also another special thing is the temporal coherence, which is like at the exact same phase, or at the exact same point, each radiation is coming out. So all the photons that are coming out, they are starting at the exact same time frame, which gives you like in insane ability to then control the laser in terms of how much energy intensity that you wanted to provide, and at what exact time you want that to provide. Because ultra short laser pulses, which is like the at the forefront of research again, and that they are very short laser pulses, and they can produce immense amount of energy because you are producing it for such small amount of time. You can have very large energy. So that those laser pulses, and even in continuous lasers, you can have very large energy, because there is like a temporal coherence. In temporal coherence, we understand it normally that omega t plus phi, if you keep the phase the same, then the temporal phase stays the same. So it will stay the same, like the width of the pulse. If you keep the width of the pulse the same, then you can have that width periodically at the same intensity, same frequency, same phase, along the direction of your propagation. So which gives you a lot of control over the energy and the phase. And once you have control over the energy, which is the amplitude, you have the control over energy, you have the control over the phase, you have the control over the polarization of light, and you have the control over the frequency of light. If you have all these controls, these knobs are basically what you get from a laser as a source. That's why lasers are very important to have in the lab, and that's why lasers are like the key sources that we use in the lab, because all these aspects we can control, and we do understand everything about all these aspects in terms of lasers. And that's why, like I said in the starting section, that if once we know the system perfectly, then we can use it, then we can control the system, then we can apply the system. So that's why we use lasers in application, and we apply them, or we use them to study atoms in our field, and we can study atoms using the lasers because the probe here is the laser, and then we are probing the atom as a system. And because the probe is very well known, very well understood, that's why we can use it to understand something else as a system, which is like as a system. Or if we also understand atom as a system, then we have two different systems that we completely understand, let's say a laser and an atom. And what we will now understand is the unknown concept of how they interact exactly, or how they interact in different environments, how they interact in different intensities, in different scenarios, in different parameters. If we change the parameters, what happens? What is the interaction? Can we control that interaction? If we understand that interaction, we can then apply that interaction to forming a system which is like quantum computing, or there are other applications for this as well. But this is how I think the journey in science goes, that first you have to understand the system completely, which is what happened with the lasers. And then you can control it, then you can manipulate it, and then you can use it for applications. So that's why I wanted to mention like what are the important facts about lasers and how to understand them, and some key points that okay, you can still imagine laser as in some different framework. So okay, that was all about lasers. So I think we don't have a lot of time, but quickly before going to density matrices, in quantum mechanics we usually deal with uh, Dirac notation. So Dirac notation gives us in terms of kets and bras, and we represent kets as, because quantum mechanics, because being a linear theory, it has direct mapping to linear algebra, the concepts that we have been studying from a long time. That in if you have a vector, if your system is like a vector space, then you can represent the states of your system as vectors. So that the analogy between linear algebra, I mean, it's not an analogy; it's the exact same actually. That linear algebra is something that is quantum mechanics is based on. But so whenever we are dealing with quantum mechanics, there are few different approaches that we can follow. We can use Schrodinger's approach, we can use Heisenberg's approach. So it's like we can either talk in terms of differential equations, we can write everything in terms of differential equations, or we can write the same equations in terms of also matrices. And matrices are sometimes very useful to do things in quantum mechanics. So then it's so that's why I wanted to mention this analogy, that it's not an analogy, it's an exact same thing, but I still wanted to point that out, that whenever you are talking in terms of kets, you have to talk in terms of like column vector in matrix analogy. So whenever you're talking in terms of kets, they are like the column vectors, and when you're talking in terms of bras, like so these are the kets. This is for like, I mean, I thought, or like my initial thought was that this lecture would be mainly targeted to an audience um, which has some exposure to all these concepts already, but they would benefit from having little refreshers in between all the time. So that's why I am catering the course such that, or catering the lectures such that I start from very basics and I touch a little bit on the very advanced topics and mainly explain you the bridge between them. So that's why I'm starting from such basics. Of course, this would be very obvious to most of you, so you can zone out, let's say, for this specific 5-10 minute review. But I guess to make everyone come to the same page, I think these kinds of reviews are really useful. That's why I prefer doing these. So whenever you are whenever you're studying quantum physics, you generally study linear algebra. It's really nice if you first understand everything about linear algebra and then you study quantum physics. Then it will be much easier for you to learn the formalism of quantum mechanics, because it is most of it is like linear algebra. So whenever you're imagining a ket vector, you should imagine in terms of column vectors, and then the complex conjugate of that, uh, the the dagger of that is the brass, which is the in this notation should must be familiar with you in matrices. So if you take a column vector, then if you take a dagger of that, you'll get a row vector. So bras are something that you can imagine in terms of row vectors. So these are vectors basically which are one dimensional. Now, if you want to, so these are generally the states. So states are generally represented by the vectors in quantum mechanics, and operators, which are the observables of our system, which is like the quantity that we are going to measure, let's say momentum or position or energies or any other potential energy, kinetic energy, or any other operators that we have. Those operators are going to be the observables that you will measure on your system. So your system already has all the energy eigenstates and all the correct base in correct basis. You can have all the information about your system, and that system, those states are represented by vectors, which are one-dimensional vectors, each of them. Okay, it need not be one-dimensional as well. It can be n-dimensional, but it's just that it is just a row vector or a column vector. If you are talking in terms of Kets and Bras, which is a really useful notation for Dirac notation is really useful when you're doing quantum mechanics. So make sure you are familiar with that, because we are going to use just that formalism or just that notation whenever we are going to do all the derivations in this course. So yeah, the states are the vectors. The operators are matrices. So whatever observables that we will have, observables are represented by operators in quantum physics, and those are what we operate on the state vectors to get all the information out of the system. And generally, it is represented by an eigenvalue problem that you have an observable A, which is an operator, which is a matrix. So it is n cross n, let's say symmetric. So then n cross n matrix. And then it is operating on a state vector psi, which is generally, it's not written like this. So to be precise, it's written like this. It is operating on the state vector. So this is the vector n, and all the matrix multiplication rules are always applicable in quantum physics as well. So then when you apply on this, you will get all the summations of whatever eigenstates or whatever basis that is. So whenever an operator is operated on a state vector, it will generally, the operator operation will generally involve its own basis. So whenever I am coming, let's say I am, so how does this formalism come from? Is generally whenever you are measuring something, if you are measuring energy of a system, let's say, and the system is cylindrical system, so then it's nice to use the cylindrical basis, because all the energy that I am going to measure, all the energy values that I'm going to measure, or the vectors, the state that I am going to measure from the system, there are only possible number of possible states that I can measure in that system. So if so basically that's the crux of quantum physics, that whenever you have a system, there are only allowed possible number of values that you can get from that system. If you do a measurement, if you are measuring energy of a specific system, then there are only a possible number of values that you can get, and there is a probability associated with each energy value. So if you have 10 energy levels, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then there is a probability that you will get each energy level with some probability, basically. So, but those 10 are the energy levels that you're going to get. You won't get anything else. So basically, in that sense, the vector space is complete, and you can span the entire vector space in terms of the basis that you have. So similarly, each operator that we are operating on a system, that comes with its own basis, and that basis is basically all the allowed values that you can have from that measurement, and then the probabilities are the coefficients that you can get from that measurement. So what is the probability of getting the specific measurement? That will be given by the coefficient of that. So basically, that's how we formulate the problem in quantum physics, that if you have an observable, if you want to measure a quantity basically about a system, then first you have to express that system in terms of basis of that observable. So basis of that operator. So that operator already, so if you have a observable, that will be an operator, that will be a matrix. That matrix already has its own eigenvectors, and it has its own eigenvalues, in the sense that it already comes with a basis, which is the correct basis in which you should express that system. Then what you do is take the system and then project it on the basis of that operator. So, this projection is like the key part in the quantum mechanics. That whenever the system already has its own basis, right? The in which we have understood that system, and the operator comes with its own basis. So then you have to project from one basis to another basis to get all the information. So it's like, so if I am standing, let's say, at a certain location. So if I'm standing at a certain location, how will you convey that I am standing at a specific location by giving coordinates? So it's like if you have a three-dimensional space, then in the three-dimensional space, you have three basis vectors, which is I cap, j cap, and k cap, which gives you the entire space in terms of x axis, y axis, and z axis. So now if you want to convey the information that, okay, I am standing at a particular location, you will give some person three coordinates. What are the three coordinates? Those are the weights by which you will give my x coordinate, you will give my y coordinate, and you will give my z coordinate. If you give all these three coordinates, that person will find me and at my correct location wherever I'm standing. So basically, what I have done in this case is I have taken the three-dimensional space. It can be anything. So it can also be, I can also express the location in terms of spherical coordinates. I can also express the location in terms of cylindrical coordinates. It has the exact same information, but it has very different bases. So you can choose different bases. But then if you are doing an operation, which is here, I was doing an operation that I wanted to find what's the position, then you can choose your specific basis, and then you can convey that information in that specific basis in terms of projecting on that basis, because now I projected on that basis and I got that, okay, I'm standing at 3 comma 5 comma 5, which means that I projected the information on this basis on x y x cap, y cap, z cap, and then the weight for each was like 3 comma 5 comma 5. So that's how you get, on projection, you get the information in terms of the basis vectors and the weightage of each basis vector. So that's like the crux of how this formalism comes in. So that's why each problem in quantum physics, generally about measurement, is in terms of eigenvalue problem. You can formulate the problem in terms of eigenvalue problem, which is like an operator is operating on a state vector, and then we get an eigenvalue, and we get all the bases with some coefficients, that are all the possible energy values, and the probabilities are associated with each of these eigenvalues. So I sort of wanted to explain that, but not um, in a way that it is taught in quantum mechanics, because some of these I am assuming that most of you are familiar with, but still it is so important that I wanted to emphasize it once in the course. That's why the formulation of eigenvalue problem in quantum physics is like a really important step, and the projection operator basically is like really crucial to all the understandings that we do later on in the course. So that's why eigenvalue problem. So yeah, kets are the vectors, the operators are like the matrices, and the solution of the eigenvalue problem is actually what we want to solve. Then, okay, what is inner product? Inner product generally in vector spaces gives you how parallel the vectors are. So if they are parallel, then the inner product is one. If they're perpendicular, then the inner product is zero. So basically, it gives you the orientation of the two vectors, how parallel or perpendicular they are. If they're perpendicular, they are called as orthogonal. If they are normalized, then they are called as orthonormal. So generally, a basis vector is generally orthonormal. What that means is the squares of all the coefficients will give you one, which is like a normalized thing. And in quantum physics, that comes very fundamentally, because in our system, the total probability all should add up to one always. So that's the normalization thing. That is the analogy with vector spaces. And orthogonal is each basis vector is orthogonal to each other, which is like here we are considering a simpler case where all the eigenvalues are distinct. Then all the eigenvectors are orthogonal to each other in the sense that they are linearly independent. So there is a concept of linearly independent vectors in linear algebra, which is very crucial, and this concept directly applies here. So basically, if you do an inner product, then you will get a scalar, which is just the quantity, which is not a vector. So if you do psi multiplication like this is the scalar, this is just a number. And if you do a multiplication exactly other way, then this is a matrix. So actually, psi is a vector. So depends how you multiply on it. So because it's like multiplying a row with a column and column with a row. So you either get a scalar or you get a matrix. And the density matrix that we are going to talk about is the matrix that is constructed generally. If it's a pure state, it is constructed from two psi, two ket vectors, and if it's a mixed state, it is a different thing. But anyway, we will talk about that. But basically, in quantum physics, you really need a basis when you're talking about things, and this is how the basic formalism of quantum mechanics can be understood in terms of linear algebra theory. But it is essential to note that in quantum physics, we are always talking about probabilities. What is the probability of getting a particular state? What is the probability of getting a particular value of the measurement? Whenever we are doing measurements, they are all probabilistic measurements because classically we have always been dealing with deterministic measurements. But in quantum physics, I think the fundamental difference is we are always talking in terms of probabilities, and we are always talking in terms of quantized energy values and the probabilities of those energy values whenever we do the measurement. So if we do a measurement on a system, first we already need to know what are the eigenvalues of the system, and then get the probabilities out, and then get the time evolution out. So actually, the difficult part is the wave function collapse. So maybe I will talk about this in some other lecture, but wave function collapse is the most difficult part to understand in quantum physics because that is something that doesn't come out of the theory. All the other things that solving the Schrodinger's equation and getting the eigenvalue spectrum and getting the time evolution, all those things are they come out of linear theory in quantum physics, but the main concept or like the main intuition comes from wave function collapse, which is that you need to collapse the wave function in the space of the basis, and then those are the only possible energy values, and then once you collapse it, it will collapse in one of the eigenvectors, and it will stay there when you perform the measurement. So after you perform the measurement, it doesn't stay in the superposition of the state, which is initially your system is a superposition of all the energy eigenstates. And once you do the measurement, it collapses in one of those energy eigenstates. Uh, but yeah, so that is like the main uh, concept that I wanted to just mention once, that wave function collapse, which is like the measurement part, is the main thing that is intuitively a little difficult to understand whenever we are talking in terms of quantum mechanics. So uh, we talked about this last lecture as well. So what is the recipe to understand the system and predict its behavior? First, you have to write down the Hamiltonian of the system. That is like the main part. And most of the time, in research, generally we have theoretical research and we have experimental research, right? So theoretical research mainly starts, or in some cases also ends at just this first step, that writing down the Hamiltonian for the system. So what exactly are the parameters? What exactly are the variables of the system that are important for us to consider? That comes from the Hamiltonian. So once you write down the Hamiltonian for the system, you already sort of know what is your system and how it depends on each variables of the system. By variables, I just mean what is the position. I mean how your energy depends on the position, how your energy depends on the momentum, um, and angular momentum and different, let's say, electric field, whatever variables you have in your system, how your energy depends on those variables. That gives you the Hamiltonian for the system. Because we have, in the last two lectures, we have talked about Hamiltonian for two-level system. We have talked about Hamiltonian for harmonic oscillator. So all the systems that we describe, once we write down the Hamiltonian's mathematical form, so that form should be sufficient for us to understand what are the behaviors, what are the important parameters in our system and the dependencies. So once we write down the Hamiltonian for the system, the second step is solve the Schrodinger's time independent equation, which is H psi is equal to E psi, Hamiltonian of operating on a psi, which is, again, if you notice, it's an eigenvalue problem. So it's a very linear problem, and it's a linear algebra problem. We formulate quantum mechanics in terms of just this problem. So we solve this Schrodinger's time independent equation. We get all the energy values of the system, all the energy eigenvalues of the system, all the energy eigenvectors. That energy eigenvector will form our basis. So that will be the basis for our system. And then once we know the basis for our system, then we get the time evolution of the system by solving Schrodinger's time dependent equation now. And then by solving this differential equation, we will get the time evolution of these eigenstates, which we have already found. So first, write down the Hamiltonian, solve the Schrodinger's time independent equation. That will give you a basis for your system. That will tell you everything about your system in terms of what are the energy values that are possible if you measure something, what are the energy eigenstates of the system, everything. So everything for the system is already known, but it's just that the system is a superposition of all those energy eigenstates. And then to get the time evolution, you time evolve it and solve this equation to predict its behavior, how it will behave in time. Because how it behaves in time depends on how much energy it has currently or how much energy it is going to exchange with the other system or the environment. So the behavior in time we can talk about a lot, and we can predict a lot depending on how much we can uh, monitor the energy of the system or how much we can write down mathematically the energy of the system. So basically what we are doing in quantum mechanics is we are first finding out everything about the system and then predicting its behavior and then doing the measurement on it. So first we need to understand the system completely in order to perform the measurement. That is the key point that I wanted to deliver in this lecture, that if we are doing a quantum measurement, the measurement process is only possible after the measurement process always comes after you understand the system completely. So if you take such a system that is already solved by this recipe that I have mentioned, then if you take such a system, then you know the outcomes already, right? That if you are going to make a measurement on that system, you already kind of know which values to expect from the system. What are the possible outcomes? So it's like if you have thrown a dice, you already know that it is going to be 1, 2, 3, 4, 5, 6. It won't be another anything else. If you are doing heads or tails, you are definitely sure that it will be either heads or tails. So you already sort of know the outcomes of the system. So if you have such a system, then you already know what are the outcomes. What remains then? Why are we doing all this? Why is the measurement even necessary? So the measurement now becomes necessary to find what is the probability of finding each measurement, or what is the probability of finding different values of the system. If you have six different possibilities in the dice, then what is the probability of getting, let's say, one on the dice? What is the probability of getting six on the dice? So it's like you can now it becomes a problem where you now only want to understand what is the probability of getting a particular state, because you already know what state you are going to get. What are the possible states you already know. So that the only question that remains in measurement is what is the probability of getting something. So that's why the nature of quantum mechanics is so probabilistic, that the only question that remains in a measurement is generally what is the probability of getting a specific value. So how is this measurement probability different than the statistical probability? Because we have talked about a lot till now that the measurement process in quantum mechanics is really probabilistic. So how how is this different than the normal statistical mechanics probability that we deal with? So I sent one video on the Telegram group which talks about this a lot, and mainly I want to introduce density matrices using the formalism that is mentioned in that video, because that's the best I have seen in terms of how to introduce density matrices. Because that video talks about, and it's I guess a 3 video lecture series. So these lectures will be along the same lines that I'm going to explain. I'm going to introduce density matrix just in the same context that the video does. So if you have time, please go through that video. It's like a 10-minute video, 3 videos of like 10-15 minutes. And those are really informative, though visually it explains you and it goes, you can stop the video, you can go really slow. It explains, it starts from a language where everyone can understand, and then it introduces the concept of density matrices really well. So I think this lecture and the next lecture will be mainly based on how that video goes as well, to introduce the concept of density matrix. Because density matrix formalism is something that is really useful to know when we are dealing with different mixtures of states that we are going to do complicated, when we do complicated systems. By complicated, I mean if you have more than one number of atoms, if you have a system that is complicated like a solid state physics system, then how to deal with those systems still doing quantum mechanics. Because quantum mechanics, since generally we started with an isolated system which is like just a 2-level system. So then if we have more than those, and if we still want to understand, if we also in that system, if we want to understand coherences, there are a lot of topics which come out as in a natural way when we are dealing with density matrix approach, compared to the normal state vector approach that we generally follow using size, Ketz and Bras state vectors. So state vector formalism is how we have been doing quantum mechanics, I think, till now, or that is how generally people start in quantum mechanics. But density matrix formalism, basically, you can do the same problems that you have done using Ket vector formalism, using state vector formalism in density matrix as well. And density matrix also provides you another framework which in which some problems get really easy. So I will just explain in last 10 minutes of this lecture. I will just introduce you why we need to talk about density matrix and what is the motivation to talk about density matrix. So there are two types of probabilities that we talk about always in physics. The two types are, one is quantum type of probability, which is involved in the measurement process itself. So it's like if you know a system very well, if you know what are the possible values that I can get if I measure something on that system, and the system is a superposition of all those values, then still the measurement has some probabilistic nature, because when you measure something, there is a probability that you will get a specific eigenstate. So that's why the measurement part in quantum mechanics also involves probabilistic nature. But in addition to that, there is also another probability that is seen a lot in physics. That is also seen in classical systems, in statistical mechanics, which is like if you have many such systems. So if your system consists of more than one number of particles, then if you have identical number of particles, if you have different number of particles which are not identical, if you have a collection of them, let's say if you take a solid, or if you take any system with like the number of gas particles, generally we associate Avogadro's number. So it's like the particles are like particles are like 10 to the 23, which is closer to the Avogadro number. So the number of particles are, if this number is huge, right? Because we were dealing with just a single atom or something. So if these are the number of atoms that you want to deal with now, and your system comprises of these many number of atoms, then how to deal with that problem? Then that problem also becomes statistically relevant, and it also becomes probabilistic because of the macroscopic nature of the system. So if we were dealing with single atoms or single molecules, that is a micro system. So you just have one system, and you don't have to worry about any other system. But if you have a collection of such systems, then if your system has collection of such atoms or particles, then this collection can be termed as macroscopic system, which consists of lot of microscopic systems. Then to deal with those, you already are dealing with probability, because it is impossible then to monitor or to predict behavior of each single atom in, let's say, if you are performing any simulations on the lattice, or if you are performing if you are studying a material, or if you are studying let's say a solid, then you don't describe that solid in terms of, let's say, how the atoms are doing, how each single atom is doing in that solid. You do it collectively, right? So what you say is, what is the heat that can be produced by that material, or what is the excitation that we can apply on the solid material or any material science system. So it's like it has a collection of so many systems, it has a collection of so many particles, that it is impossible to monitor each behavior of, and that doesn't even help. So it's important to then collectively understand that system, and then because we are understanding that system collectively, it is like a statistical mixture of all the small systems. And then when you have a statistical mixture of all small systems, then you have to talk about probabilities, that what is the probability of getting this final energy, because you have already seen that the probabilities are, we relate the probabilities with when if you are talking about finding energy E, then in statistical mechanics we always talk about this term, which is e to the power minus E by kT. So if you are defining energy in terms of temperature, if we are defining it in terms of what is the probability of getting a specific energy for a solid, then you don't have to talk about each different atom. So that is how probabilistic nature comes in when you are talking about a specific energy level. But that energy level is a combination, or is a superposition already of many different atoms together. But you don't have to understand each single atom. So that's why my macroscopic systems, like classical systems, already have this probability associated with them. But understand the difference between these two, that probability comes in very different context in classical systems, and in quantum systems, in addition to the classical ones, there is already inherent probability, which is probabilistic nature of the measurement itself. Even if your system is a single atom, it will still involve probability. So that's what I wanted to motivate. So in the first system, in the quantum system, basically, if you have a single system, then the measurement problem has the probability involved with it. So we have the complete information about the system. So if we are operating an observable on the system, this is the observable. If you are operating on a system which is this is a state vector of the system, then we can express in terms of energy eigenvalues. Even for a two-level system, it will be just C1 U1 plus C2 U2, let's say, because you have two states, two energy eigenstates of the system for a two-level system. So it's like you will have those two values with the coefficients. So you can express them in a linear combination, and that will give you the information about the entire system. So the system in first case is completely known, but in the second case, which is the classical case for a macroscopic case, it's not that we know each individual atom and its energy eigenstates. We don't need to know. So that's why it's like you have a partial information about the system. So there are two different types that I'm talking about. So for the second type, we have partial information about the microscopic particles of the system. And in this macro system, which is like solid state system, then you use statistical mechanics, and then probability comes into the picture, because you already had some incomplete information about the system. So even if you have complete information, you have some probabilistic nature in measurement. And if you have incomplete information, you have additional probabilistic nature in your measurement. So that's why these two types of probabilities are what we deal with when we are talking about measurement process. So how do these compare now? Then this is like the last point that I will make. Then I will stop in like 5 minutes. So if you take the first system, when you're having a single atom or a single two-level system, then you already know that there are only two energy levels and there is a probability associated with each energy level. So you take a system, let's say like this psi, which has two energy eigenstates, and like the basis has the two elements, and each one is has a coefficient associated with it. So when you have this as a system, if you have a two-level system, which is like inherently a quantum system, which is a single system, and then the psi is written in terms of psi 1 and psi 2, which means that it is a superposition of all the energy eigenstates. Then this is your initial psi, so this is your system. So then if you are going to do a state selection, like which state I'm going to be in, so now if you have just one atom, then you don't have this. By state selection I mean, if you are selecting a system out of these, then because you have a single system, there is no state selection, so this step is actually deterministic. So since you have just one system and you will choose one from one, you are not you will not have any issues choosing between those, because it's like it's only one system between which you are choosing. So this system is just one. So when I'm saying states, it has two energy eigenvalues, but both of these are just in superposition. So it is actually talking in terms of just a single state. So that's why we have just one state. And when we have a two-level system, if we consider that as a system, then we know everything about the system, but the state is the superposition state of these two energy eigenvalues, and that is the psi that I'm talking about. So the first step of state selection is deterministic here. And then if we want to now perform measurement on it, so what is the probability of getting a value lambda 1, and what is the probability of getting a value lambda 2? Because if I perform measurement on the system, I am only going to get either lambda 1 or lambda 2. There is no other value that I am going to get if I perform energy measurement on this system, because there are only two energy eigenvalues. So the two energy eigenvalues are then possible with each probability is coefficient square. So you will get either energy eigenvalue lambda with a probability P1 that is given by C1 square, or you will get a probability P2, or you will get a eigenvalue lambda 2 with a probability of P2. So now this step is probabilistic. So the measurement process is probabilistic. So the first step was defining your system. Second step was state selection. And the third step is measurement of the system. So this is like the recipe for a measurement. So then in this recipe, the first step was deterministic in terms of the quantum system, which is a single system. And the second step was probabilistic. And now if we take a classical system, which is a statistical mixture of many particles together, let's say, then we have, let's say, n1 copies of a system psi1, and we have n2 copies of system psi2. So now it's like imagining that we have n1 particles of, let's say, bosons and n2 particles of, let's say, fermions, which is like all of them are identical for, let's say, all of them are identical. But even if all of them are identical, there is a combination of them, and the total system that we have is a superposition, incoherent superposition of all these. So what do you mean by incoherent superposition is they are added in terms of probabilities and not amplitudes. So if you have a copy of such systems, it's like if you have a Avogadro number of particles in your system, instead of only one particle that we had here, if you have these many number of particles, then you can represent them as statistical mixture. And here, when you're choosing the system, which is this, so if this is your system, so this is step one, and then now you're doing state selection. So now you're going to choose which of these systems that I can take from. So I can take, so if because there are like 10 to the 23 particles, I can take one particle of them out of those, and the choice that I have to choose from all these particles will be like 10 to the power 23. Out of those, I have to choose only one system. So the choice now is probabilistic. And what is the probability then? is that the probability is like the coefficient C1 can be given as, so there is a probability that I can choose a boson, there is a probability that I can choose a fermion. So what is the probability of choosing those is this is the coefficient, and coefficient square gives us the probability. So in this case, the probability comes in the first step itself when I'm choosing the state, because out of 10 to the 23 particles, I can either choose a boson or I can either choose a fermion if the system consists of just bosons and fermions. Then what is the probability that I will choose a boson is C1 square. What is the probability that I will choose a fermion is C2 square. So there are two different systems that I can choose from. So in the first step itself, the first step was probabilistic. Now, once I know that psi1 is a boson, or let's say a boson with just one energy level or something, so then if all of them are just single energy level, then I know that the measurement process, the third step in the measurement process will be deterministic. So now this step becomes deterministic. So all the energy, all the particles were with the same energy levels, with the same energy. So all bosons had the same energy. All fermions had the same energy, which was different than the boson energy. But the probabilistic nature came here in the first step itself when I was choosing either from a boson or fermion. And once I knew that, okay, this is a boson, then I directly know what is the energy of the system. So that second step is deterministic. But you can see that both these systems, the statistical mixture, classical statistical mixture, and the quantum measurement of a single system, both had probabilistic nature in the measurement process itself. But there were different points where we had to introduce probability, and these two frameworks are actually very similar when we are dealing with the problem. So the final answer is actually the same in both cases, that you will get energy eigenvalue lambda with a probability that C1 square, and you'll get energy eigenvalue lambda 2 with a probability of C2 square. So the final answer is actually the same, but the framework is very different. One framework is classical statistical framework, and another framework is quantum measurement framework. So the first formalism involved superposition, and the second formalism didn't involve superposition. They were incoherent mixture, but still we get the same probability. And the power now, the power of density matrix approach is that you can solve essentially the same problem uh, with system 1 or system 2. You can solve both of these in density matrix formalism and you will have no problem. And also you can have a system where you have 10 to the 23 particles and each particle has a superposition of eigenstates. Then basically, which is like the real system. In real systems, you have both these kinds of probabilities in your problem. So then if you have both these probabilities in your problem, you can still solve the problem by using density matrix formalism, which was not the case is initially, because if you are dealing with psi, if you are solving everything in terms of state vectors, then incorporating this classical statistical mixture, incorporating these classical probability concept in quantum mechanics becomes non-trivial. So it becomes complicated when you are, or becomes very difficult to solve when you are solving using state vectors. But in the density matrix formalism, it becomes really easy to go from one framework to another framework, or even incorporate both frameworks in your problem, which is in real systems, which we have these two kinds of probabilities. In everyday life, we already deal with both these kinds of probabilities. So we should be able to solve a problem which involves both these kinds of probabilities. And we will tackle them using density matrix formalism. But why do we need density matrix formalism is like, this is the motivation why we need density matrix formalism in the first place. And in the next lecture, we will see that actually the first formalism is for the pure state, which is the purely quantum mechanical state. And the second formalism is for the mixed state. I will explain what exactly I mean by pure state, what exactly is a mixed state, because mixed state is like the incoherent superposition and pure state is like the coherent superposition of the eigenvalues. But I will elaborate more on this. But the first formalism is for the pure state. So basically, so now I have just told you that why density matrix formalism is useful to have as a tool while solving problems in quantum mechanics. So next time, what I am going to talk about is how we can use this density matrix formalism, or first of all, what is density matrix formalism? How we can write Schrodinger's equation in density matrix? Why? No, I think why I have okay, how we can deal with mixed states, how we can deal with pure states in using density matrix formalism. That is where I will start. And then I will try to explain you how that formalism takes us from state vectors to a complicated system understanding. So I think that's the formalism, that's density matrix formalism, and I will derive what's the use and how coherences inbuilt come in superpositions, and how we can incorporate them using density matrix. How is the density matrix formalism for a pure state? How is the density matrix formalism for a mixed state? I will explain that in the next lecture. And I think next lecture we'll be covering three things. First is density matrix formalism. I will complete everything about density matrices. Then like a short overview of whatever we have done till now, because everything till now is just a build up for the main derivation that we want to do in this course, which is the light atom interaction, Hamiltonian. Once we understand these three concepts, which is harmonic oscillator, two level systems, and density matrix approach, if we know all these three, then we will be able to grasp everything that is there to grasp about the derivation of how an atom interacts with the light, when we will treat atom as a two-level system and we'll treat light as a harmonic oscillator, how this interaction happens, and what are the results of this interaction, and how to represent or how to understand the results in terms of different formalisms. So that's why in the next lecture, I'm going to cover density matrix formalism for pure state and mixed state. In this lecture, I just wanted to motivate why the density matrix formalism is useful. Hopefully that is conveyed. But next lecture, yeah, I will give a short overview of whatever I explained today in terms of density matrices. And I will derive for pure state how we use density matrix. I will derive how for mixed state we use density matrix. And then in the next lecture, towards the end, we will start the derivation that is there in the seventh chapter of Christopher Foot's book, which I am going to follow. That book is something that I will follow for that derivation, and we will go slowly in the derivation. But in order to start that derivation, I think these three topics are really essential for us um, to understand and to appreciate or to follow that derivation. So that's why I spent so much time on these three concepts. Each concept I think took one or two lectures. So, but maybe for those who have gone through this formalism already, uh, all the lectures up till now were just an overview of these three topics. So yeah, I mean, so for this lecture, I just wanted to explain the motivation behind density matrix, and also wanted to give you like discuss with you a short summary on lasers and on the fundamental concepts that we use in atomic physics. So, okay, so I think that's it for for today's lecture. In the next lecture, I have already told you what are the topics I'm going to cover. I will post this lecture note on the Telegram group and also on the Google Classroom. If you have any doubts, feel free to email me. If you have any doubts, also you can message me on Telegram. But yeah, make this course interactive so that we also get to know whether you are understanding, whether the pace of the course is fine or not, because some of the discussions that we did today were little advanced. So maybe some of you will feel that we were out of place in the sense that we went too fast in today's lecture or not. So if you felt like that, if you want to go slowly, then we can also do that. So please let us know whenever you can in the feedbacks, and please submit that assignment, because I am going to read whatever you guys will post. and that will give me a good understanding of whatever you have learned so far in the course. Because if some concepts are missing from whatever you submit, then those are the concepts that I will again go through with little more detail so that no one misses out on any of the concepts. So, okay, yeah, please submit that assignment, and I think that's it for today's lecture. If you guys have any doubts, feel free to stay right now as well after the call and message me anytime. But I think that's it for today's lecture. Unless anyone wants to ask any doubts, I'm free, but I think I can declare that today's lecture is done. So if I don't know whether Nitin sir has joined. If Nitin sir is there, okay, he has not joined. That's fine. Yeah, if you guys have any doubts or if you want to discuss anything with me, feel free to unmute yourself and discuss. Otherwise, the lecture is done. I'll post the lecture note on the group. Thank you for joining today.